Ladies and gentlemen, dear guests, welcome today. Our visitor teacher, Jacopo Ciambella, today he is going to introduce magneto-elastic instabilities in soft actuators. He came from to the Sapienza University of Rome, and he is going to introduce this topic with detail. Have a good day.
Thank you very much. Thank you very much to all of you for being here for the second time in a few days. I hope you won't regret it. And today I will talk on a completely different topic, which is, as your colleague said, magnetoelastic soft actuators. Okay, magnetoelastic instabilities. This is a research topic we have been looking at for the past few years. It's not only me. So we have collaboration with University of Bristol, and in fact most of the experiments I will show you have been carried out there by David Stenier, who was doing his PhD at that time. And we have collaboration with Samir Ratekar in Cranfield, and two colleagues from Rome, Antonino Favata and Giuseppe Tomassetti. And more recently also with Paola Nardinocchi from my same department. So what I meant during this presentation, I will show you briefly, I will touch the following topic. So these are elastomers. What I will show you are elastomers reinforced with fibers, magnetic fibers. And so we will talk about all the aspects from manufacturing of the specimen to the mechanical properties, how the mechanical properties can be controlled according to the orientation of the fibers, and how this object can be actuated by applying an external magnetic field. But let us start with motivations of the research. Okay, so when we initially start looking at the problem, we were only interested in the mechanical aspects. So how to control the mechanical properties of a specimen by tailoring. Stiffness can be tailored by controlling the orientation of the fiber locally. And so what we wanted to do was small strain, because we start looking at this field in epoxy-based composite, so everything was small strain, and we were interested in controlling the orientation, stiffening a small strain, but why so? Because we were looking at different possible applications. So actuators that can bend, like this one, can twist, or for instance magnetic hinge, something like that. So think about a specimen that can completely bend over, okay, like a hinge, or even micromotors. So a sort of what I will show you at the end of this talk is very similar to a flap-like motion of this actuator. So something that can be used to make movement of objects inside a fluid. Okay, small objects inside a fluid. The material we used in most of the presentation is Pdms, so a silicon elastomer, very soft, reinforced with carbon fiber. Not exactly carbon fiber, but as I will show you, nickel-coated carbon fiber. Why the nickel coating? Because these improve the magnetic properties of the fiber. Consider that we are talking about young moduli of the order of 10 megapascal, so relatively soft material. So to make a very short summary of the goals of this work so we wanted to control the orientation of the fibers. We want to exploit anisotropy to have controlled mechanical properties, and we wanted to use actuation. So I'd be able to actuate this sample. And this is a classical example where you, by controlling very well, so by controlling the orientation of the external fiber in the tube, the internal pressure, you can obtain different type of shape motions of the actuators. And this is reminiscent what we are trying to do here on what is normally carried out in standard composite material, epoxy-based composite, where they, with a technique which is called VAT. VAT stands for variable angle toes. So they have this technique where in epoxy-based composite, they're able to steer the fiber within a plane, within a ply of the composite, with an external machine. And so they do something like that. So they start with a certain orientation, and then at the other side of the specimen, they obtain an orthogonal orientation. And this is exactly done for stiffness, for tailoring the stiffness of the material. And so once you do that, you can control the viscoelastic properties, for instance. You can also control the band gap. So if you imagine to use this system to study wave propagation, so the wave propagation properties will be different here and here, and maybe you will be able to control, to tune the band gap of the system. There are examples in the literature of this. Something similar has been already done, of course. This is the examples I was talking you before. So this is a pressurized tube with external fibers, and according to the direction of the fibers, they were able to obtain those shape I showed you before, those motions. But there are also physical and natural systems that use fiber orientation to obtain different actuation pattern. This is a work by Herb group, where they essentially mimic the behavior of natural system like pine cones, and by controlling the orientation, for instance, in this case, the actuation for this system, in this system was inner pressure, the control parameter. Here the actuation was obtained by diffusion of a liquid. So you pass from this configuration to this configuration by wetting your specimen. So essentially the humidity entered the specimen, so there is a diffusion process, and that specimen will bend. Why it will bend? Because you have fiber in the different section of this small strip oriented differently. Okay, so different stiffness, and then will give you this bending effect. And the same with another distribution of the fiber, you can get twisting. Okay, and always by diffusion of a solvent inside the material, of humidity of solvent. Then something very similar, what I will show you, has been carried out in this by Kimura group, and they use, I think they use silicon rubber reinforced with steel rods. Okay, and what they obtained, they started with this very nice distribution of the steel rods. They apply a magnetic fields, and they ended up having this deformed configuration here. Okay, and we will tell you more about this later on, because this is exactly the same physical mechanism that I will exploit in this presentation. Normally, when you orient reinforcement inside a material, you also control the mechanical properties. This is an example of, this is an epoxy base where they use what they call ultra-high magnetic response particle. So these are platelets-like particles which has been treated to respond to the magnetic fields, and they were able to orient them, okay, and they obtain different tensile properties. For instance, if the particles are oriented along the load direction, they've got a much higher stiffness way in a composite material. The most common way is by shear processing, so extrusion. If you have a viscous solution with fibers, when you extrude this viscous solution, the solution will pass through a nozzle, and this will naturally orient the fiber, because the size of the nozzle is very small, and it's almost comparable to the fiber size, and so the fiber will get aligned. Or you can either do tape casting, so layer by layer deposition. Also, this process will give you some orientation of the fiber. You can do ultrasonic assembly. If you have a viscous solution and you send into this viscous solution an ultrasonic wave, the ultrasonic wave can be tuned to have orientation of the reinforcement inside this viscous solution. But this is normally carried out only for very small specimens. Then you can use electrical field or magnetic field. Why magnetic field? Magnetic field is contactless compared to electrical field, so you can do that remotely. And also you can achieve very complex shape, because if you use nonlinear magnetic fields, which are very easy to generate, imagine the magnetic field generated by a cylindrical magnet. A very simple cylindrical magnet generates a nonlinear field, where the field lines change with the space. And this is exactly what is done here. You can't see very well, but this is a specimen where the magnet, the cylindrical magnet, is underneath this point, okay, vertically aligned. And then you see that the fibers initially are bent over the plane and then starts rotating towards the magnets there. Okay, so around this region they are vertically aligned, so they are going out the plane of the projection. In this region they are aligned within the plane of the projection. So you can simply obtain very complex fiber pattern with the magnetic field. And so the idea was to exactly study this process, the reorientation process, to have a very fine control over it. How to do that? Well, so I will show you a very simple model to do that. First of all, let me introduce some notation here. So what I will do, I will assume that the particle is ellipsoidal. And why so? Because you have some advantage. From the magnetic point of view, you can solve Maxwell equation in closed form. And from the mechanical point of view, we want to study the motion of this particle into a viscous solution. And so you can work out the drag coefficient in closed form if the particle is ellipsoidal. So the field is H, the magnetic field outside the particle is nonlinear, so the field line can bend. Inside the particle you have what is called B, the magnetic induction, and M, which is the magnetization of the particle. And with small n here, I will indicate the main axis of the ellipsoid, so which will give you the orientation of the particle at time t. And as you can see here, there will always be a mismatch between the orientation of B and the orientation of M. And so what will happen from the physical point of view is very simple. It's the principle of the compass. Okay? M wants to rotate to be parallel to B, right? And this is the main mechanism. So these particles want to rotate in a way that M and B are parallel. Some simplifying assumption of this, the material is assumed to behave linearly magnetic. It means that it's either paramagnetic or diamagnetic. It means that if you double the field, the magnetization will double. Okay? And so the fiber, as I said, has an ellipsoidal shape. We will study the quasi-static motion. So we won't solve the Navier-Stokes equation for this problem, just quasi-static motion. And also we will assume that the particles are dilute, so there won't be any particle-particle interaction. So in this setting, you can define the magnetization of the particle, which of course depends on the induction field, as this expression here, where B is the external field. These are material coefficients. Mu 0 is the permeability of the vacuum, as usual. N is the direction of the particle. Okay, this is the dyadic product, by the way. And then you can also define the energy, the magnetic energy of the particle, which has two terms here. One which only depends on the intensity of the field, B times B, this is the inner product. And the other one which depends on, as I said before, you see on the inner product between the direction of the particle and the field. Okay? This coefficient here is called anisotropic susceptibilities. And different material can have different anisotropic susceptibilities. What happens is the following. Key A is positive. Okay? If the field is uniform, this is a constant term. So it doesn't matter in your equation. Okay, let us assume for a moment that the field is uniform. You can have two possibilities. Either Ka is positive, meaning that the material is paramagnetic, and this means that what is happening. These are the field line. The particles will orient parallel to the field line. Why? Because Ka is positive, and you have a minus sign here. So when n is parallel to B, this quantity is maximum. Right? And so you have a minus sign, so the energy is minimum. This is a configuration which is a minimum of the magnetic energy. On the opposite, if Ka is negative, the material is called diamagnetic, and because of this minus sign, the energy is minimum when the particle and the magnetic field are orthogonal. Okay? The fiber we use are paramagnetic fibers, mostly, so they will orient parallel. But in principle, you can have a mixture where you use either paramagnetic and diamagnetic, so some of them will orient perpendicularly and some of them parallel to the field. Then you have more complex situation where you have ferromagnetic material. I didn't talk about ferromagnetic material, but for ferromagnetic material, the relationship is much more complex because the relationship between magnetic induction and magnetization is highly nonlinear. Let's write some equation of motions. Okay, very simple. We have the magnetic force, which is the gradient of the potential, the magnetic potential I showed you before, and the magnetic torque, which depends on the cross product between N and B. Nu here is the volume of the particle. Once you have the force and the torque, you can write down the equation of motion. V is the translational velocity of the particle. Omega is the rotational velocity along the secondary axis. So what it means secondary axis, that we are not taking into account rotation around the main axis of the particle. We are not interested in those. Okay? So in the equation of motion, you have this coefficient, d parallel, d orthogonal, and d theta, which are nothing than the drag coefficients. Okay? Because remember, this particle is embedded into a viscous fluid. And because the ellipsoidal shape, as I said before, these drag coefficients are known in closed form, or at least in approximate form. So L, in fact, is the length of the particle, AR is the aspect ratio, and eta here is the viscosity of the solution. So we can do something more. For instance, take a viscosity which is changing with time, because this is exactly what is happening when you manufacture the specimen. Because you disperse the fiber into the specimen when it's still viscous, but then it starts to solidify, okay, becomes solid. It's because the composite is curing. So you can assume that the viscosity is increasing with time exponentially. So when the viscosity is infinite, it means that the material is fully cured, so it's solid. Eta 0 is now the viscosity, the initial viscosity of the solution, and tau c is what I call here characteristic curing time. Okay, so you can change very easily. So you put this expression in previous equation, you get the translational velocity, equation for the translational velocity, and notice that this equation only depends on the gradient of c, so on the force. The rotational velocity only depends on the mutual direction between n and b. Okay? But this can be solved in closed form, for instance, and everything depends, the orientational time, for instance, depends on a characteristic time, which I call here tau O. Tau O is a characteristic orientation time. The expression is here in closed form, but I plotted it here in terms of the aspect ratio of the particle. So what is happening is that if you increase the aspect ratio, the orientation time of the particle is increasing. So the particle will take, for a given magnetic field, B0, the particle will take, longer particle will take more time to orient with the field, okay, with this relationship. What happens when the field is uniform? As I said, this is quite a peculiar situation, but it's very interesting from the experimental point of view. Why so? Because when you do your composite, you would like to have a homogeneous structure. So you would like to have particles which are uniformly distributed, control only the orientation. So homogeneous material, but anisotropic. And if you have a nonlinear field, the particle will start moving. So you will end up having agglomeration of the particle somewhere in the specimen, which is not very good for the mechanical properties. Whilst when you have a uniform field, it's completely different, because you start with a homogeneous distribution of the particles, and these particles will only rotate in place. And so we'll end up having a homogeneous distribution of particles with a tailored orientation. This is exactly what we wanted. Okay? And things get very easy when grad of c is 0, so you have no force. You see the first equation here cancel out. So you don't have any translational velocity, only rotational. And so if you restrict yourself to this problem, here it is, you only have one scalar differential equation that governs you the orientation of the particles with time. Okay? Tau r is the reduced orientation time, and everything depends on gamma, which is the ratio between the curing time of the composite, how much time needs to be cured, and the orientation time of the particle. Very simple equation. So what happens when gamma goes to 0? What does it mean? It means that the curing time is much longer than the orientation time. Okay? On the opposite, when gamma is very big, it means that this composite cures very fast. So as I will show you, as expected, the particle won't have time to orient themselves. You can work out the solution. It's a ordinary differential equation, linear, so very easy. You can work out the solution in closed form. And this is the expression of the orientation angle, C here, which is the angle between the particle and the field line with time, tau r. Okay? And this is what is happening for different gamma. So very small gamma means very large curing time. So the expected solution would be C equal to 0, meaning that the fibers are oriented. Okay? And so when gamma is very small, these fibers have time to orient themselves with the field. It goes to 0. When gamma is very large, 100, they don't have time. So they start orienting, but the composite cures. So the viscosity, they can't move anymore. And so this, you can work out the equation. It's one-dimensional, so the problem is everything can be carried out analytically. You can also work out the distribution of the fiber, how the distribution of the fibers evolve with time. So if we assume that you have an initial distribution which is uniform, 1 over pi means that there is a uniform distribution at time 0, you can work out the distribution, we can work out the distribution at time tr. So, and you end up having this expression here, which is plotted here. Okay? So on this axis, you have the particle direction, c, which goes from minus pi over 2 to pi over 2. On this axis, you have the time. Okay? You start with a uniform distribution, so all angles are equally probable. And then what is happening with gamma equal 0.5, so a relatively low gamma, the particle will orient around 0, and you end up with most particle oriented around 0. If gamma is larger, meaning that the curing time is very shorter, you start with a uniform distribution, but we end up with a distribution of the particle much wider, meaning that you have not all the particles have time to orient themselves. Okay, so the scattering, the angle is much larger. Okay, what you can do with this? You can calculate, for instance, the probability of having a certain fiber within a certain orientation in closed form, and this is quite interesting because it is useful to work out this B0 min. That expression gives you the minimum field you want to apply once you know the properties of the matrix. I recall you that eta 0 is the initial viscosity of the matrix and tau c is the curing time. So these quantities here only depends on the matrix. This depends on the magnetic properties of the particles, and these other are only related to the geometric properties of the particles. Okay? This equation gives you the minimum field you have to apply to obtain a certain orientation. Let's say, for instance, that you want that 90% of particles are oriented with the field within a plus minus 5 degree. Okay? This equation gives you the minimum field you have to apply for a given matrix and for a given aspect ratio of the particle. Here I plotted in red a region where you need to apply a magnetic field higher than 1 Tesla. Okay? Why higher than 1 Tesla? Because more than 1 Tesla is very difficult to obtain experimentally. Okay? I want to give you a matter of comparison with this table. Okay? These are experimental results. Okay? Different type of matrix, different type of filler, and this is the field intensity. So now consider that with a proper assembly of cylindrical magnets, neodymium magnets, which are quite strong magnets, you can obtain fields up to 0.1 Tesla, let's say, no more than 0.1, probably even lower. And so this is what is done here. Then 8 Tesla is extremely, you need a huge equipment to obtain 8 Tesla. In the experiment I showed you before where they used steel rod to obtain the bending of that beam, they use 8 Tesla. Then you can go over 10 Tesla is, with 10 Tesla you can make a frog levitate, for instance. And with 40 Tesla, 25 Tesla is the MR machine. So huge field. So in all our experiment, we were well below that 0.2 Tesla, okay, with our material. So very simple experimental setup. This is what we use. Let's see some experimental results now, our results. So the filler are nickel-coated carbon fiber. The length is 0.25 millimeter, so aspect ratio around 50. Why we use nickel-coated carbon fiber? Because they are inexpensive, they're easy to manufacture, they can be bought from the market, and they can be because of the nickel coating, the field you need to apply is relatively low. As I said, we won't go up to 0.1 Tesla, but no more. PDMS is extremely easy to find, it's inexpensive, so it was the first elastomer we had to test. The problem with PDMS, as I show you, is not easy to stitch something to get to PDMS, so it's very difficult that the interaction between the matrix and the fiber is to get a very good interaction. Okay? In fact, as we have seen in our experiment, sometimes the fibers were pulled out, completely pulled out from the matrix, okay, because the interaction was not very good, some of them. How did we get the orientation? So what we did, we used an electromagnets. We poured the solution of PDMS and fiber within the platelets of the electromagnets. We turned on the electromagnets and the particles were oriented. And we manufacture a specimen with different orientations from 0 to 90 degrees. Okay, this is an example where the fibers are aligned. You can't see very well, but there are red fibers which are aligned pretty much. We also observe fiber agglomeration, which is detrimental for the mechanical properties. And consider that the percentage in volume, I think it's written here, was only 6% in volume. Okay, I didn't mention that, so relatively low percentage of fiber reinforcement. These are the results in terms of the orientation. This is exactly the equation I showed you before, which give you the orientation of the fiber at time tr. And this is how the fiber orientation changes with time, after 20 minutes, after 60 minutes, after 150 minutes. So as expected, the shape of this curve increase, so more particles are orienting around 0 degree, but not all of them are. Why so? We asked them ourselves why, and this is what we thought is happening. So due to the processing of this fiber, many fibers were broken and many fibers lost their coating. And if they lost their coating, means that you need to apply a much higher field to orient them. And so this is our explanation. And in fact, if you modify this equation by adding with a certain rule of mixture, so you imagine to have a certain percentage of fiber which are able to orient themselves and a certain percentage of fiber where no orientation occur, you get a much better fitting. Okay? And so this suggests us that we had to improve our manufacturing methodology. So one of the ways we used to disperse fibers inside the PDM was sonication. And probably sonication was not good for the coating. Okay? And so we extract the magnetic susceptibilities by fitting those experimental data, and what we observed was that we had a magnetic susceptibility was almost 20 times higher than standard carbon fiber. But this was expected because these are not standard carbon fiber, these are coated with nickel, which is a very active magnetic material. Okay? Possible upgrades, we didn't consider the distribution of length. All the fiber were 0.25 millimeter, but you have a certain dispersion in the length. And the dispersion affects the orientation time quite drastically. So you can improve this model by taking into account the distribution of length. Now, very briefly, I want to touch what happens when you have a nonlinear field, okay? Because this is interesting also from the experimental point of view, although very difficult to control, okay? Because magnetic fields are very nonlinear fields, okay? And so when you have nonlinear fields, you have either translational velocity and rotational velocity. You can do the same calculation with this model, and you have I put here some dimensionless quantities, okay? And what you have, this rotational velocity depends on this, what I call generalized force, which is composed of two terms, okay? And these two terms, one depends on the BR is the normalized induction field. One depends on the gradient of BR, how nonlinear the field is. The other terms depends on the gradient of N, okay? So how these fibers the orientation of the fibers change with the plane. Luckily enough, these two coefficients, this is 1, and you have this coefficient here, are drastically different. You can do some approximation of this equation, meaning that if I call this coefficient Ki, normally for paramagnetic or diamagnetic material, this Ki is much larger than 1, meaning that the expression of the force becomes this one. So only matters, in terms of force, only matters the gradient of B, how nonlinear the field is. It doesn't matter the orientation of the particle. It's an order of magnitude lower, at least. Okay? And so you have a simplified expression which is this one. No? So the rotational velocity only depends, as before, on the mutual orientation between n and br. The translational velocity depends on what? Depends on this parameter Ka, which I said is much larger than 1, and depends on, of course, on the aspect ratio of the particle. But what is interesting is that the ratio between these two velocities is independent of the matrix properties and the magnetic field intensity. Okay? Only depends on the geometric properties of the particle, right? So the ratio between translational velocity and orientational velocity only depends on the geometric properties of the particle and not on the matrix properties, so curing time, viscosity, or the magnetic field strength. So let's do some example. As I said, we use cylindrical magnets. The cylindrical magnet is here. This is the field intensity. The contour plot represents the field intensity, and you can also see the field lines. Okay? Why we use cylindrical magnets? Because for cylindrical magnets, you know the expression of the B field in closed form. So you can work out this equation of motion almost analytically. And so this is what happens when you have a particle here, initially in this position, and what I plot here is the position x and y with time. So this is 0, 0, meaning that, as expected, both x and y diminishes. Okay? So the particle is being attracted by the magnets with time. And here is the orientation velocity. Sorry, is the orientation of the particle. And this is the direction of the corresponding field line. So what is happening, the particle starts with a certain orientation, 60 degrees, and with time, as expected, it orients parallel with the field line. Okay? So this model predicts this behavior, which is quite reasonable. Okay? Different position, different behavior, of course. And the nice thing is that everything here is in closed form. Then we do Monte Carlo simulation, so we put a lot of particles here because this is to reproduce our experimental setup. So rather than electromagnets, the advantage of using an electromagnet is that within the platelets of the electromagnets, the magnetic field is uniform. And by controlling the current, you can also control the intensity. With cylindrical magnets, of course, you cannot control the intensity, but you have nonlinear fields, so you have bending of you potentially can bend the fibers within your specimen. And so what you have is the following. We have different Ka. Remember, this is essentially give you the magnetic properties of the particle. Ka equal to 1, this is what happens after 15 seconds, 30 seconds. So the particles why this simulation? Maybe I wasn't very clear before. So what we wanted to study was to find an optimal configuration which allows you to have particles rotating within your specimen according to the field lines, but with a very low translational velocity, because you don't want to have particle agglomeration. So ideally, you only want the particle to bend with the field lines, but no agglomeration. And for instance, with Ki equal to 1 is okay. With Ka equal to 100, you start seeing agglomeration here, particle agglomeration. And this would be detrimental for your specimen, because the mechanical properties close to the border will be very bad. And so with this simple model, you can maybe find, we still haven't done this experimentally, but maybe you can find configuration of the magnets where you have an optimal ratio between the translation and the orientational velocities. And this is our idea. Okay? Find an optimal configuration, either in terms of particle shapes, so aspect ratio, and also position of the magnets. This is a simulation done with a software for magnetic simulation, which you use finite element. You have two cylindrical magnets here, and this is the one which is oriented with a certain orientation with respect to the other. Okay? And these are the field lines. So once you know the field lines, you can work out the ratio between the velocity and see if that setup is good for you. So now let's go back to mechanics. Okay, everything was magnetic. Now let's go back to mechanics. So what are the mechanical properties of this material, right? And so we did use, initially we used electromagnets, then we used this very simple experimental setup with neodymium magnets. We bought the neodymium magnets on eBay. Why so? Because at the end the magnetic field was much higher than the one obtained with the electromagnets. So the intensity of the field is written here, you can't see, but it's 0.04 Tesla. Okay? I said 0.1, no, it was 0.04, much lower, so 1 over 100 Tesla. So this was the Petri dish when we pour our solution, and then we cut the specimen in the standard dog bone shape, okay, with these sides. And so you can see here fiber orientation. The magnetic field was in this direction. So the white fibers are okay. The blue fibers are not oriented, probably because they lost their coating. And then you have also fiber agglomeration, which is not very good. This is a micrograph. Okay, we use carbon fiber also for another reason, because we started playing with carbon nanotubes, because you can get nickel-coated carbon nanotubes. But the problem with nanotubes is that it's very difficult to control the orientation. Not only control the orientation, but to see the orientation of the nanotubes. To check if the nanotubes are oriented, you need much complicated equipment. Here is simply a microscope. Okay? You can see the orientation of the fiber almost at naked eyes. This is 1 millimeter, for instance. So the mechanical properties. Here, no, I skip something. Here it is. So we did DISG, of course. So we pull our specimen and we measure stress and strain. So standard quasi-static experiments. And these are the results. So this is an elastomer. So we arrive at 60% of deformation, which is nothing for an elastomer. But for our experimental setup we had in mind is more than enough. And these are the effect of the orientation. 0, 30, 60, and 75 degrees. So as expected, you have an increase of the Young modulus when the fiber are oriented. But you should notice that the fiber at 75 degrees are somehow weaker than the 30 degree one. Okay? So 0 degree means that the fibers are in the direction of the right. So 0 degree means that they are in the direction of the load, sorry. 90 are perpendicular direction. And so this is the 75 are, and so what struck us most when we saw when we saw these results is that the 0 degree and the 30 degree had very similar Young modulus. But these are to be expected indeed. I'll show you why. So we did some modeling of this in Abacus, okay? We did multi-scale modeling actually in Abacus. What we did was that you have these things here. So you have a representative volume elements with a lot of fiber inside. You apply a deformation F, which is simple extension. So you pull in the direction, lambda is the stretch here. And because of the Poisson ratio, because the matrix is incompressible, you have lateral striction of the specimen. And what we wanted to do, the problem here was the following. So standard transversal isotropic model in nonlinear elasticity are taught for very long fibers, okay, for fibers which span the entire representative volume elements. Our intent here was to assess what were the effect of the fact that the fiber is much shorter than the representative volume elements. So there should be some border effects. Okay, we wanted to assess that. So the matrix was Mooney-Rivlin materials, and what we did was we also simulate a single fiber here, an RV with a single fiber. Okay, the same thing. We apply the deformation and we have the stretch. And so what we wanted to do, compare the macroscopic stress here, and this can be used for this. You can use a standard transversal isotropic model. because you can think of this like an homogenized material. You have lots of fiber, all with the same orientation, so you end up having a transversal isotropic material with this being the axis of transverse isotropy. But to check if this model is good for this type of composite, we also run simulation on this level, and we compare the two stresses. This was the idea. So how we did the single fiber model, so is and why we wanted to do the single fiber model, because first of all has a reduced computational cost compared to the entire specimen with the fiber. You can use this either for purely multi-scale problem. So in multi-scale problem, what you do is at each element, at each material point, you have to solve a microscopic problem, which is exactly that one. So what we did, we use a Python routine to make the microscopic level and the macroscopic level communicate in abacus. The model for the at this level was compared with a standard transversal isotropic model. The energy of a standard isotropic model in nonlinear elasticity is this one. Essentially, you have these two terms, which I1 and I2 are the first two invariants of the deformation gradient. So this is standard isotropic nonlinear elasticity. Okay? And we have an additional term which depends on I4, which is the stretch along the fiber. Okay? How much the stretch how much the fiber are stretched. And so this is the elastic energy. So you impose this form of the deformation, which is simple extension, and the fact that the determinant of f is equal to 1 is because the matrix is incompressible. That's the incompressibility constraint. You can work out the stress in closed form, and then you can compare this numerical simulation with this analytical model. Okay? And this is what you have. So you have a very good agreement between the two models. Again, this was expected, but not so much, because the fiber, I recall you, the fiber are short. Doesn't span the entire volume element. And this is interestingly, this is the Young modulus in the direction of the load, 1. So this is loaded in this direction. And this is the corresponding Young modulus. So you have a maximum at 0 degree, as expected, but then the minimum is not at 90 degree. It's around 60 degree. And this depends on the fact that we enforce, I believe, plane stress. Okay, this is in plane stress. And then you can look at how the orientation of the fiber changes with time. Okay, because the fact that you are pulling this specimen in this direction, this fiber will tend to orient with the loading direction. Okay, so this is the orientation. A fiber which is initially at 90 degrees, perpendicular with the loading direction, won't change its direction. So it will stay at 90 degrees, as expected. The same is true for 0 degree. It's already oriented. The other, of course, will change the direction, but the analytical model is quite good at predicting this behavior. And also the energy. Okay? We compare the macroscopic and the microscopic energy, so the energy predicted by the numerical simulation with the energy predicted by the model. Okay? And so these are the numerical simulations, and the plane is the analytical model, so there is a very good correspondence. So this means that you can use the model I showed you before to fit the experimental results without doing numerical simulations. So the analytical model will be enough. And in fact, these are the results in terms of this model here. So it fits well the behavior up to 30% of strain, and then starts to diverge. But for our scope, 30% was more than enough. Okay, I will show you why. And this is the behavior of the tensile modulus compared to the fiber angle. Okay? These are the experimental results. So it worked pretty well. Okay? So the conclusion of this part, the perelastic model can be used quite well. We saw some divergence between the model and the experimental results. We think that this is due to the fact that the interaction between the fiber and the matrix is not very good. So for strain higher than 30%, there is you will have detachment of the fiber from the matrix. So the mechanical properties are lower than expected in the case. And what you can do to solve this problem is silane coating. When you have Pdms, you can do silent coating to improve the adhesion of the fiber within the matrix. Then you can, of course, you can improve this model. This is a very simple transversal isotropic model. For instance, you can take into account the orientation spread within the specimen. Now there is no orientation spread, no fiber distribution. And also you can, in principle, take into account the orientation in the fiber length. This would be a nice extension of this analytical model. Okay, affect the magnetic field. We didn't see from in terms of Young modulus any significant effect. We tested the material, but we didn't see any significant effect in terms of Young modulus. Okay, so what we did the tensile test under magnetic field for different orientation. But in terms of effect, up to almost 0.1 Tesla, there was no significant effect. Okay, we are almost done here, so we are probably here. Now I try to jump your attention on this loop, okay, by showing you this result. So as I said, we started by looking at how the specimens are manufactured. We look at the mechanical properties. Now we want to look at the actuation properties. So once you have this material, and the material is solid, you can actuate the specimen by applying an external field. So the fibers are freeze in the matrix. If you apply the field, the matrix will deform to allow the fibers to orient with the external field. This is a very basic principle. And this is what is happening here. This is a real specimen in a cantilever configuration. So this point is fixed, is suspended within these field lines here. So if the fiber are 0 degree, means that they are oriented in this direction. You obtain bending. If the fibers are 90 degree, in this case 90 degree means outside the plane of projection, you will obtain twisting. Okay? And so by modulating the orientation of the fiber, you can pass from bending to twisting. And this would be very nice. So you can have a flap that can either bend or twist. Okay? And so why this happening? Why this is happening? So now I want to try to explain this effect, which was kind of unexpected. So I'll show you some experiments. Okay, this, as I said, this is our specimen. These are the plates of an electromagnet. Okay, the field is uniform, and these are the field lines. In this case, the fiber were oriented at 0 degree, meaning that along the specimen length in this direction. And what we did this experiment. So we switch on the electromagnets, we start increasing the field, and nothing happened up to a certain value of the external field. You can see it again, nothing happened, and then, bam, it bent. Initially, the deformation is almost 0. Okay? This is quite strange behavior. We didn't expect to see this. We were expecting to see a slowly bending according to the field lines. But then, again, up to 0.06, and then it bends immediately. And the same thing happened for this other specimen here, where you have fibers at 90 degrees. Again, 90 degrees means they are orthogonal to the field lines in this direction here. Okay? This is, again, clamped. This is a free hand. And this is what we have seen. Nothing happened. But then at a certain level of the magnetic field, which was different from the previous one, the specimen twisted immediately. Okay? And why so? Then we try to interpret these results with a simple model. Okay? So the specimen is actually a very thin specimen, so we use beam theory, large strain beam theory. We didn't need to do 3D nonlinear elasticity, because these are very thin strip. So can be well described with the beam theory. In the beam theory, you have an elastic energy, large strain beam theory, which depends on theta prime, which is the curvature square, plus the derivative of the twisting angle square. So you have 2 degrees of freedom, theta and phi. And this is the abscissa along the beam length. On top of this, you have also magnetic energy. And because of as I said before, because the field is uniform, the only term in the magnetic energy is the one that weighs the mutual orientation between the particle at position S and the magnetic field, B. Okay? And so the total energy is the sum of these two. you can work out the Euler-Lagrange equation for this problem, so the governing equation of this problem, and you have n in terms of the initial angle, theta and phi. Theta, I say again, is the bending angle, and phi is the twisting angle of the specimen. In our experiment, B was directed along y. Okay? Was in this direction here. And so you can do stability analysis, for instance, because the total energy is nonlinear, okay? Because of this sinus here. Okay, you have in this equation you have cosinus square, so the governing equation is nonlinear. You can do nonlinear analysis, and then you can approximate the energy at the fourth order, because we want to study stability. And once you have that, you can study the stability of the solution by looking at the Hessian of the energy. So if the energy is convex or non-convex. Okay? And the nice thing about this simple one-dimensional model is that you can work out the critical field at which you have instability. Okay? I didn't say that explicitly, but that behavior we've seen before was an instability. So the specimen remained still up to a certain critical value of the field when you had snap. Okay? Immediately deformation. With these very few equations, you can work out the critical field in closed form. And these are again experimental results. Okay? These are experimental results. So in terms of magnetic field, this is the 0-degree specimen. Okay? And this is the bending angle here, and this is the twisting angle. No, sorry, this is only bending angle, because for 0 degree we didn't observe any twisting. So you only have bending. Okay, how the bending angle changes with the field. And so what we see is this, it bend a little bit, but a little bit up to a certain value of the field where you have bend, an immediate bending. So the bending angle increased abruptly. The same happened for, this was 50 degree. B is 45 degree, 75 degree, 90 degree. In 90 degree, you also always see this jump in the deformation, but you only observe twisting, very little bending. And so these are the fitting with the model. Okay? You can see here you have the critical field in terms of the fiber angle, initial fiber angle. These are the experimental results, and this is the prediction of the model. Okay? So I should say that it works quite well in predicting this behavior. And again, the model works pretty well in predicting also the bending and twisting angle. So the yellow line is the bending angle predicted by the model. This is the twisting angle predicted by the model, and the dots are the experimental results. And so this model explains why that was happening. Again, I'll show you here. So essentially, the specimen the fiber were initially at 0 degree. The specimen was straight, right? The field line in that configuration are perpendicular to the fiber, to most of the fibers. And so if you work out the torque acting on the fiber is 0 in that case. When the fibers and the field are perpendicular, the torque is 0. Okay? But that's a configuration where the energy is maximum, the magnetic energy. So what we did, we start increasing the intensity of the field. We start increasing the magnetic energy. And so the straight configuration, because we were pumping magnetic energy into the system, the straight configuration becomes unstable, meaning that the specimen prefers to bend rather than stay straight. And the same happened for the twisting angle. In that case, again, the fibers were initially orthogonal to the field lines, so it means 0 torque and 0 force. The specimen wanted to stay straight, but you are pumping magnetic energy in the system, and so you arrive at a certain point when the specimen prefers to twist rather than stay still. Okay, this was the mechanical effect we described. And so we did that. So I would just want to summarize. This simple model allows us to describe this instability effect. What we wanted to do now is to try to do more complex fiber distribution. So distribution in terms of theta, for instance, where the angle varies within the flap direction. Okay, and also we want to develop algorithm which allows you to pass with the same specimen to pass from bending to twisting, to have a flap-like motion. Okay? This is the idea. We haven't done that yet. So let's conclude here, briefly summarize what we have seen so far. From the experiments, we have shown the possibility of orienting nickel-coated carbon fiber with an external magnetic field, short fiber. We have seen small and large strain effects, strain hardening effect. Then from the modeling point of view, we have seen that a model which, a nonlinear model which depends on I1, I2 and I4 is enough to describe the experimental behavior. And in theory, you can introduce the effect of the magnetic field in Abacus or in other software to describe complex deformation. The deformation we have seen so far are very simple. Now what are the challenge we are working on now? Achieve complex fiber distribution by using nonlinear fields without having fiber agglomeration, and also in the model account for stochastic distribution of the fiber length and orientation. These are our goals now. Okay, so thank you very much for your attention, for being here. These are some reference on this topic, very recent reference. Okay, thank you very much. Okay. Yep.
For example, right now you're actuating, well, the main focus is actuating the fibers, controlling them magnetically.
Mm-hmm.
Do you consider the fiber concentration and how does it affect the
We-
mechanical behavior of the actuator?
We did test, yes, we did test different fiber.
Is there an optimum percentage for the fiber loading?
I mean, the higher the concentration of the fiber from the magnetic perspective, the better is, but can be detrimental for the mechanical properties. But consider the deformation of this specimen were very low, because the specimen was very thin. So it is true that the displacement is high, but the deformation is very low. So we were not concerned, for instance, for the fact that the interaction between the fiber and the matrix was not good, because we didn't expect to have deformation higher than 10% probably. And but the problem with the higher volume fraction of the fiber are the manufacturing. So you can either get fiber agglomeration if you go higher than 6% in volume, or you can also have difficulties in mixing, sonicate the solution. So the fiber will stitch all together. So we didn't manage to get above 6% for manufacturing issues. That was our limit.
So you use the fibers like called viscous, right? Composite with viscous.
Aha, yes, that's true, that's true.
So is there any option to control this beam with the local points, not with the whole beam? So we actuate this beam,
Mm-hmm.
and we make this dance, right? With bending or twisting.
Yes, yes.
But we apply to the whole beam, and we made it for the whole beam.
Yes. So you want to control locally?
Yes.
This is a good question. I mean, if you have the proper equipment, this specimen was very small, so it's a matter of scale. Okay, the specimen was 27 millimeters, so 2 centimeters. But if you have a right equipment, you can, in principle, control the magnetic field locally, very, very close to the specimen, with a probe, something like that. And this would help with the local orientation for manufacturing. I'm not sure if we will help with the actuating thing, because for actuation you want to stay far away from your specimen, because imagine that you can scale down this process, okay? And imagine that you want to use this for moving an object in your vein, okay? In your vein, what happens is that you have an external field which is on a larger scale than the scale of the vein. So the field is almost uniform. So, I'm not sure that it's convenient from the from the actuating point of view. It's definitely convenient for the manufacturing point of view. So you locally control the orientation. This would be very, very interesting. But I think that kind of equipment is quite complex. Okay. Thank you very much. Thank you.